Awesome. Thank you for your presentation, Raphael. Thank you for and for the question. Maybe we will be able to continue with Olivier for the second paper presentation. Okay. Olivier, I'm giving you the mic. Do you want me to remind you of some time during your presentation?
Yeah. Yes. Thank you. Yes, maybe in 10 minutes or stuff like that.
Okay.
But I'm pretty sure it will be shorter. So
as you want.
So so I will try to do it in English too. So excuse me. I hope it will be intelligible. So for my part, I'm Olivier. I'm working at 𝗏𝗏𝗡𝗏𝗏𝗏. 𝗏𝗏𝗡𝗏𝗏, it's a French startup which is tackling the goal of live video translation and enrichment. So 𝗏𝗏𝗡𝗏𝗏 started with an offline platform where you can upload a video and it will voice clone, transcribe, translate, put your video in the your transcription, your video, and recreate a new one in the translated audio with your own voice and resync the lips behind it. And now it's called Equos because it changed of name because we are tackling the problem of live streaming. So we can enrich video streams, for example, from broadcaster, TV shows, Twitch or stuff like that, with a lot of metadata, etc. So we are bringing also lip sync and stuff like that into live. So let's see a bit how lip sync works, and you will see that after two examples, you will understand that every kind of lip sync frameworks is every kind of the same. Just some little diff which make all the sense, but all the performance. But basically, it's not so complicated. Why I say that? Because when I started, before I started to join 𝗏𝗏𝗡𝗏𝗏, I was like, oh, I'm sorry, but I have just no idea how it can work. I never did that before. So I took some time to look on the paper and say, okay, so now I see how it works. I want to work with you. And here I am. So let's go back in 2017 with 𝗏𝗏𝗏𝗏𝗏, which is one of the most popular network at this time, where a single network is trained on a single person, so on the face of Obama. The goal is to take as input the audio and to produce a video of Obama with the lip sync accordingly to the audio. So to do that, the idea is to put several blocks behind the other. And the first one is to transform the audio into some representation where a network can pass through. So it was before 𝗏𝗏𝒏𝗏𝗏 and stuff like that. So we had to pass it to into spectral features. So when I say spectral features, you can think about spectrogram and MFCC. It's more or less the same. It's you take your temporal audio and you try to create some 2D map on how the audio at different frequency evolve. And from the spectral audio, you learn some LSTM or recurrent neural network to try to predict the mouse shape. In fact, here it was not the full mouse shape, it's just only 5 PCA components, because the mouth, it's like maybe 20 key points or stuff like that. And it's a lot correlated. When you move up one lips, generally the second one will move down, and all the pixels are really correlated together. So instead of trying to predict 20 key points, which correspond to 40 floats, because you have X and Y, you just have to predict 5 values. So it's much simpler to learn. And from those 5 predicted values, you can use your PCA in the inverse way and try to repredict the mouse shape. And from this new mouse shape, you just have to put it on your image, put the mouse shape, and learn a network to map from this image on the lower hand to the upper hand. So how did they do that? It was like a Pix2Pix 1 year ago. So they reused the Pix2Pix with the units, but without the GAN loss, just the L1 regression. And they didn't needed to put the GAN loss because they thought the results were good enough. and no temporal consistency stuff is added neither. So it's just one frame, one audio frame, a little bit of speech, produce one image by producing an intermediate mode representation. So well, every frame is generated and can be generated independently. So it's good for a first start, but the issue with that is that you are trained only on a single person, and when you want to train, for example, on myself, you need to relearn a new network to do the painting from Obama to myself. So another newcomer, few years, maybe 1 or 2 years after, which is quite fundamental in this kind of architecture, is 𝗏𝗡 And the idea is to do accurate talking ellipse in the wild for any ID and any voice. So unlike Obama, which is only Obama voice to Obama face, you can speak and I can animate, I don't know, Louis' mouth to make it say whatever I want. And they had also to introduce new metrics for the evaluation of such a task because before the way it was done was more like with traditional metrics like PSNR, SSCM or stuff like that, which is not really good for this kind of task. So before them, the idea, they start from the constat, from the, well, let's say constat, that the pixel loss, just L1 loss, is kind of a weak judge to know if the lips are sinks. In fact, the lip, when you try to reconstruct, it corresponds to something like less than 4% of the reconstruction of the image. So even for the training, they found that half of the training is just trying to put the right pixel on the skin, and only the second half the network try to start to learn how to morph the lip accordingly to the audio. First, the stuff they remarked. Second stuff, it's that papers before, like LibGAN, the discriminator, they found it that it was only 56% accurate to detect off-sync audio lips pairs. So it's not so good for building a lip sync. And they proposed to use another lip sync expert. So the title of the paper was "A lip sync expert is all you need." And this lip sync expert will be 91% accurate to detect the off-sync lips audio pairs. Another stuff previously they want to tackle is that it was like a single frame learning, no temporal consistency. So when you generate frame by frame without learning to smooth between the frames, you have some kind of jittering effect, which can be harsh when you look at it. So from those two main remarks, they propose to use this lip sync expert, which will be used as a second discriminator. It's an adaptation of the SyncNet, which is a paper from 2016 from 𝗏𝒏 and Chung, and which is taking as input its two-branch network, one for audio, one for face, and with some L2 distance, they are able, it's trained to say, oh, if sync, it's well sync, or no, it's off sync. And some of the adaptation that they added, it's now it's taking as input, wow, color images. The network is deeper, yes. We skip connection, yes. ResNet was just 2 years ago, and made a little change in the loss function, which is like cosine similarity between the embeddings, then passed through the binary cross entropy. And this network is trained only on the half lower of the face. And they kept this discriminator frozen during all the training. Why? Because when they looked at the LibGAN discriminator, they found that it's mainly focused on some artifacts on the images to distinguish if the image was generated, so fake or real, like a GAN, but it was not the purpose that they wanted. They wanted something which would tell if the images was real, generated or fake, and something, another discriminator, which is more like temporal consistency or the lip sync in sync with the audio. And so in the architecture, as you can see, you have as input in one branch your spectrogram, my spectrogram segments in the green branch. Then you passed to the blue branch some heads, so up to 5 frames, and with the inpainted mouth, and it's try to reconstruct. And as you can see, the loss will be concatenation between the L1 reconstruction loss, the discriminator like in LibGAN to say, oh, it's look like a real image and not a generated image, and the pre-trained lip sync expert, which is kept frozen during all the training. So L1 reconstruction loss again, because like peaks to peaks, they found it in the paper at the origin. It was producing images which are a bit less blurry than L2 reconstruction. They introduced some kind of temporal windows of 5 frames. So as you can see here in the concatenation, so it's a bit smoother, the moves, and add another discriminator, the GAN discriminator, alongside the signets to have images which are less bits blurry. And the final loss, you can see, just like the linear combination of those 3 terms, kind of trade-off between quality and sync. They found in the paper, if my memory is still not too bad, that's the GAN version is a little bit less lip sync, but produce nicer results visually, and vice versa. For the evaluation, the idea is that before the networks were trained with some PSNR and SSCM, so more image quality metrics, which are quite old but still used a lot, but which are not made at all for lip sync error measure quality. The other metric which is quite used is the FYD, which is more like introduced for the GANs, at least democratized for the GANs, which is made to quantify the realism and the diversity of the images generated, to say, oh, it's look nice and it's still in line with my datasets, my training datasets. And the other metric which was used before, which is more like a lip sync metric, it's the landmark distance. So you have your face, you have your face, and you have some key points, and you measure how much the reconstructed key points are close to the real ones. But it's not focused on the lips, and as you can see, there is more landmark outside of the lips, so it's kind of inaccurate, especially for generated face, and it's not so good metrics. So they propose to use a SyncNet as metric and propose 2 metrics derived from this, the distance and the correlation between the audio and the lips. Note that the SyncNet is the original one, the one from Jung and Zisserman, not the modified version, because it's kind of bit of cheating if it's at the same network you use in the training, and there is some kind of adage or stuff like that, or the Goodhart law or something like that, which is something that if you use some metric as subjective, it stop to be a good metric. I don't know if it was really clear. I feel like François Hollande speaking in English, so let's cross fingers. So so we saw the first architecture, which is Wave Tulip, and we'll take a little look to Dynet, which is a bit more recent, which is from 2023, and which is quite interesting too, and very similar to the previous one. So as input for your audio encoders, they use some deep speech features, but it's still some audio, and they didn't use really because they pass it through some audio encoder. So there are some version on GitHub where they are removing the deep speech and just replace the audio encoder with some Wave2Vec or stuff like that. So you have one branch with the audio, which is producing the 128 dimensionality audios. You have some reference frames, 5 you take at the beginning of the videos, with some lips open, closed, etc. and which will be used as some reference for the reconstruction. So the idea is that on your real image, you remove the mouth part and you try to find a way to deform those reference images such that it lies with the sound it hears. So I don't know if it's really clear like that. Blah, 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 blah. Let's see for this image. Yes. So you have your source image, you can pass it in source features, but the idea is to try to reconstruct the real mouth from a linear combination of this mouth. So, but those mouths are not really aligned with this position of the head, the eyes, and stuff like that. So the idea is to try to find the way to reposition it and to take the right lips move accordingly to the audio. So they introduce, no, they used, because they introduced in the previous paper, this layer, the 𝗦𝗽𝗲𝗶𝗃𝗃, what is the name? Some kind of spatial deformation operators to do that, which is like affine deformation of all the channels of these reference frames. So Jack, you see, well aligned, then deformed, and they try to reconstruct it. And for the training, the loss function, it's a combination still again of several loss, which is first a reconstruction loss, which here they call like a perception loss, because it's a bit more like, than just a reconstruction loss. It's like you take the output of a VGG network at different inner level, and you try to put your L1 reconstruction between all these, the real and the generated image. So it's like L1 norm at the end, but also a different intermediate representation of the VG network. It's like a naive version of the perceptual loss 𝗵𝗶𝗏𝗏. Voilà. So this will be our L1 loss plus plus. And they do it in two different sizes. On the original head size, frame size, and in the, a smaller size. So it's more consistent and they also, for having a bit more realism and more sharp images, they use some kind of GAN loss. Here it's a least square GAN loss, and they train it on both single frame learning and 5 consecutive frames, so they can have some nice temporal consistency. And also a simple lip sync loss, which is the SyncNet again. They found it that using this kind of deformation produced much better results than just fully in painting, because it's much simpler to learn that than trying to reconstruct every mouth point pixel independently, since here it's like a combination of the right rotated mouth features. What can I say more from that? I think it's good. So it's pre-trained in a single frame setting. So from a little chunk of audio, you try to predict one frame, and at different level, in more like in a program fashion. So first they train to predict the frame very little. For example, I don't remember exactly the numbers. So let's say 32 by 32, then try to predict in 48 by 48, then try to predict in 96 by 96. I don't remember exactly, but it's this kind of training. And after they have trained something to produce one frame from some audio, they just fine-tune with some temporal consistency, so that the SyncNet loss with the 5 consecutive frames, so it's a bit more less jittering between the frames and more consistent with the audio lips. The regularization here is used. The limitation of this work is that it works only on frontal images, because the dataset was just frontal images. So if you're like that, it doesn't work at all. and no big moves. So if you're moving too much in the video, it doesn't work neither. But take a better data set and maybe it will work better also. So as you can see, the framework, it's kind of the same, the previous one. It's more or less a concatenation of different losses, reconstruction, GAN for fidelity, and some temporal consistency for smoothing between the frames. But you can change some blocks, and now you have even papers which are based on diffusion. So sky is kind of the limit. So for example, two little examples here, it's when you try to change the decoder, because here everything is trained from scratch. The feature encoder is trained from scratch, the audio encoder also, and the feature decoder also. But the idea is sometimes you can use some pre-trained network which already have nice capabilities for image generation, such as a StyleGAN, to have nicer images here. So here it's what StyleSync is trying to do. And since StyleGAN is a bit complicated compared to traditional GAN, they need to make some modulation in the W plus space, but it could be a paper per se, a presentation per se, because as it will be lost a bit. And here, just another example, will not going down here, but just to see that it also works with some diffusion networks and stuff like that. And so voila, the main idea. And with this kind of technology, you can build some useful stuff like that, or much sillier projects. So for example, I show it to you, Louis, for the 1st of April. Very good project. You take a picture. Oops, I need to change. It doesn't work. Much better. Myself. Use. And by changing the audio you can find in the inner dimension, you can just start blooping, hoping it will work. Voilà. Why lip sync could be useful. It was clear enough because my English is not really good, but let's cross finger.
I loved it. Thank you so much, Olivier, for this presentation in depth of not one, but many papers on the lip sync subject. We see that you know a lot about it. I saw earlier there was a question from Raphael in the chat. Maybe I'm giving you the mic.
Yeah, I was just wondering, you talked about reference images that were used. And I was wondering, like in an inference setup, if you can actually improve those reference images by selecting within the already shown frames, maybe selecting the 5 frames that were most similar to the one we are tackling.
Yes, in fact, it's more like the most dissimilar.
Okay, because you want
the maximum variability, because when you reconstruct, it's a reconstruction by doing some kind of linear combination of those frames. So I tried several stuff here with this architecture. So for example, if you give always those 5 exact frames, it doesn't know how to open the mouth. And it gives better results if you take the most dissimilar frames, since it will be able to interpolate all the VSEMs here. And yes, the frames the reference frame need to be your face too. I try to see if I can cheat and take other people's reference frames. So before the beginning of the video, if I have enough variability, I can cheat and take some other people. But no, it will reconstruct with not the right skin color or beard or facial attributes like that.
Okay, thank you.
But the network it's quite nice because it's super small and super fast. For the trade-off quality, fastity, really nice. But need to be retrained, because as is, the results are
what speed does the network works? What's the latency he has?
Oh, I don't remember exactly the numbers, but it's much, much, much faster than real time. It's maybe 10 times faster or stuff like that. So yeah,
Impressive.
when we tried, we are not using this architecture, but at the beginning, when we are protesting not protesting, when we were trying different kind of architecture to see which kind of direction we should took, we try to optimize the maximum and cut a lot of stuff inside of it. And there is a lot of improvements you can do to fasten the inference at the end.
Awesome. Is there some other question from the spectators? Yes, ma'am?
I have a question. Which one is more difficult between the detection of mass position like this or the generating the movement?
I would say that generating the movement, because the phase detectors and landmark predictor take them all the shelves, so it's not my fault. So no, I would say that the most movements, because you need to have some kind. It's hard to be in sync, not too blurry, but not too sharp, because at every frame it will make some different effects. Yes, definitely the most movement.
I have another question, sorry. Do all models use the same time scale? I mean the time windows, you know?
A lot of models nowadays rely, for example, as audio encoder, something like 𝗴𝗏𝗡𝗏𝗏𝗏. So since they do not retrain from scratch, it's the 𝗴𝗏𝗡𝗏𝗏 audio time step, or the other model they are taking as input.
Okay. Thank you.
Thank you.
Awesome. I will share with everyone in the chat a link to a feedback form where you can give us any feedback on what you liked most, what you would like to see again, subject that you are curious about, or even if you want to present one subject yourself. We are really pleased to host many speakers for this event. It's really a pleasure for us to make the community grow by sharing knowledge together. Once again, I want to thank a lot Olivier and Raphael to have shared their expertise both today, and also for having taken time to prepare something really nice so we can all learn things together. Thank you so much.